In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about models for nuclear fusion in the solid state. It was written by Peter Hagelstein and Metzler and their colleagues from the Massachusetts Institute of Technology, Cambridge, USA, and also University of Cambridge, UK, and also Switzerland. This article presents a theoretical framework for enhancing nuclear fusion rates in solid-state environments under near-ambient conditions, drawing on quantum tunneling, electron screening, and resonance energy transfer. The study proposes rate enhancements of more than 40 orders of magnitude for deuterium DD fusion in palladium lattices. A generalized nuclear decay model describes a fusion fission process as a result of energy transfer between deuterium and palladium mediated by lattice vibrations. Practical challenges such as the coherence, destructive inference, receiver decay, and achieving resonance between a donor and receiver systems are addressed. Experimental strategies to validate the model are proposed along with its implications for the advancement of solid-state fusion as a potential pathway to sustainable energy technologies. The contents would be initiated by the introduction and its subsections such as operative definition or readily observable fusion as used in this article. This next one is nomenclature. When referring to deuterium fusion, earlier reports to energetic particle emission from metal hydrogen systems as low energies. The next one is nuclear fusion rate calculations, general fusion upon collision, spontaneous fusion from tunneling, and electron screening. The fourth chapter would be quantum dynamics of nuclear fusion in condensed matter. The fifth chapter is quantum dynamics of nuclear fusion in condensed matter, detailed treatment. From a comprehensive Hamiltonian describing nuclei in a lattice to nuclear decay model, excitation transfer dynamic between D2 and resonance receiver nuclear state transfer rate estimates D2 to helium 4 nuclei, PD or palladium nuclei as a receiver systems transfer rate estimates deuterium to palladium nuclei. The effect of high power transients in the lattice modes on excitation transfer rates, transfer to multiple palladium transitions, and meeting the resonance conditions, constraints on coherent dynamics from decoherent and loose channels, transfer rate, estimates deuterium to multiple palladium transitions, excitation transfer between deuterium and multiple receiver states. The next one is excitation transfer between deuterium and multiple receiver states with oscillator energy exchange. Transfer rate estimates deuterium to multiple resonance receiver states with oscillator energy exchange. Palladium star excited state stabilization, palladium excited state decay, other reaction products, and outlook. The next chapter is auxiliary section for detailed quantum dynamics calculations, and its subsections would be relevant deuterium, and helium-4 nuclear states and their wave functions. Now, helium-4 excited states, gamma factor, and fusion rate calculations. Derivation of indirect coupling coefficients in decay model excitation transfer, loss and reduction of destructive interference for transfer from deuterium donors to helium for receivers, loss and reduction of destructive interference for transfer from deuterium donor to palladium receivers, relativistic phenomena, nuclear coupling, selection rules estimating the matrix element for the deuterium helium 4 transition, Estimating a matrix elements for the HD helium-3 transitions, estimating a matrix elements for palladium star palladium transitions, driving minimum and maximum decay enhancement factors, parameters for magnetic dipole coupling in excitation transfer from D deuterium donors to helium-4 receivers, parameters for electric dipole coupling excitation transfer from the D2 donors to helium-4 receivers, parameters for relativistic coupling in excitation transfer from deuterium donors to helium-4 receivers, parameters for relativistic coupling in excitation transfer from deuterium donor to palladium receiver. Proton, neutron, and alpha removal energies of the stable palladium isotopes, estimating nuclear density of states for palladium nuclei, estimating generalized nuclear density of states for palladium nuclei. Nuclear molecular cluster sets, deuterium molecules in palladium and in the deuterium peroxide, the coherence, time and decay state, fragility, excitation transfer to multiple transitions, model developments for excitation transfer from deuterium to multiple receiver states with oscillator energy exchange rates between palladium and oscillator modes, analytic approximations for excitation transfer from deuterium to multiple receiver states with oscillator energy exchange. Optical phenomena and plasmon exchange, average oscillator energy exchange during excitation transfer, decay enhancement with excitation transfer to multiple receiver states, excitation transfer from the HD helium 3 fusion transition. Now I want to go through the overview. Nuclear fusion has remained a prime topic of interest since its discovery during the early 20th century. It represents a comparably clean option to access nuclear binding energy with typical fuel reaction products that in nuclear fission, and symbolizes the achievement of greater degrees of control over transmission of elements. The non-property of palladium to absorb hydrogen into its metal lattice led researchers as early as the 1920s to contemplate the effect of the condensed matter on fusion processes. Subsequently, rapid progress in plasma science led to a shift of attention toward achieving fusion in plasmas via high temperatures, and long confinement times. This was a route that could be described theoretically through comparatively simple and well-established formalisms. The hope was that associated technical challenges could be overcome in due time. Much progress has been made in the study of nuclear fusion and the plasma state. However, many challenges remain, especially in review of the scalability and economics of proposed concepts for commercial power production. Whether the simple two-body formalisms used to calculate nuclear fusion rates in plasmas remain appropriate for modeling fusion under all circumstances has been called into question. In 1965, Tarrant and Baldwin in Reference 8 pointed out that nuclear, when coupled to shared modes in a lattice, must not be treated in isolation, but call for modeling via many-body formalisms prevalent in condensed matter physics and quantum optics. The events of March 1989 added much fuel to such considerations, which electrochemists Martin Fleischmann and Stanley Pons announced experimental observations of heat beyond chemical level emanating from electrochemically treated palladium deuterium samples. Fleischmann and Pons received criticism for dearth of documentation that surrounded their experiments, at least in the early days after their initial announcement in Reference 11. However, Some leading experts in nuclear physics and quantum optics, including Edward Teller in reference 12, Julian Schwinger in reference 13, and Giuliano Preparata in reference 14 recognize, irrespective of the experimental details, that the results reported by Fleischmann and Pons were at least in principle conceivable when considering more complicated many-body formalisms to model nuclear fusion processes beyond the well-established but simple two-body formalisms. This position is reflected in Julian Schwinger's assertion. I have asked myself not whether Pons and Fleischmann are right, but whether mechanisms can be identified that will produce nuclear energy by manipulations at the atomic, the chemical level. Of course, the acceptance of the interpretation of their data is needed as a working hypothesis in order to have quantitative tests of proposed mechanisms. In our group, we have long advocated for and pursued a two-pronged approach in reference 16 experiments that claim accelerated fusion in solid-state environments need to become better characterized and documented, and theoretical models aimed at explaining such processes need to become more and more quantitative and compatible with realistic assumptions. The work here now represents for the first time to our knowledge a detailed and comprehensive argument on how nuclear fusion can be accelerated to observable rates in solid state samples at ambient conditions. The framework draws on and combines known physical principles such as quantum tunneling, electron screening, and excitation transfer dynamics underpinned by the application of a generalized nuclear decay model. This approach leverages the interactions between nuclear and lattice oscillations such as phonons and plasmons to facilitate energy transfer between donor nuclear, for example, deuteron pairs, and receiver systems, for example, groups of palladium nuclei. Palladium nuclei, with their high density of excited states, are identified as suitable receiver systems, enabling rapid energy transfer and corresponding fusion rates that extend into the observable range. The study also addresses practical considerations such as suitable and realistic lattice structures, decoherence, energy loss, and lattice dynamics. The resulting models not only match reports of accelerated fusion rates but also imply a large range of different reported reaction products, including nuclear particles and excess heat consistent with experimental reports. By bridging theoretical predictions with experimental relevance, this work seeks to lay the foundation for advancing nuclear fusion in the solid state towards a mature field of study with the impactful technological applications, which was described in reference 17. The structure is as follows. The section 2 outlines the operational definitions, nomenclature, and historical context of low energy nuclear fusion between the solid state physics. Section 3 discusses the quantum dynamics involved in nuclear fusion, including collision models and spontaneous fusion processes. Section 4 provides a simplified explanation of the complex quantum interactions between nuclear and lattice oscillations that facilitate energy transfer. Section 5 describes the core of this document, explores in-depth theoretical models and calculations that describe excitation transfer dynamic essential for enhancing fusion rates. It also proposes experimental strategies to validate the theoretical models and explores the practical challenges and implications for advancing solid-state fusion technology. An earlier version of this document first appeared as supplementary information for reference 18. Now I want to go through the introductions, operative definition, or readily observable fusion as used in this article. Here we derive estimates for deuterium-deuterium fusion rates corresponding to experimental observable that are macroscopically and uncontroversially detectable. Such experimental observables can include the emission of neutrons and charged particles or production of thermal energy that far exceeds the chemical potential energy available in the system. In terms of neutron emission, Jones and his colleagues in 1989 in the reference 19 report and observed fusion rates of 10 to the power of minus 23 or 1 per second based on neutron detection of 4.1 positive negative zero point 0.8 multiplied by 10 to the power of minus 3 counts 1 per second for ground counts minus background counts at a neutron detection efficiency of 1 and positive negative 0.3% for a 3GTID2 sample comprising about 4 multiplied by 10 to the power of 22 titanium atoms and about the same number of d pairs, a somewhat higher fusion rates of 10 to the power of minus 21 per second would be readily detectable. More generally speaking, we considered 100 milliwatts to be a power level that is readily measurable. For instance, the release of 100 mW in a 3G metal sample in ambient air at 25 degrees of Celsius leads to temperature increase of about 20 degrees of Celsius, translating to nanoscopic units. 100 mW is equal to 100 m joule per second is equal to 6.2 multiplied by 10 to the power of 11 mega electron volts 1 per second for deuterium-deuterium fusion. 23.8 megaelectron volts of energy is released per reaction considering ground states helium as a product. Therefore, the above corresponds to 2.6 multiplied by 10 to the power of 10 fusion reactions per second. A 3GTI D2 sample comprising about 4 multiplied by 10 to the power of 20 titanium atoms and approximately the same number of d pairs, then 100 milliwatt of observed power release corresponds to deuterium-deuterium fusion rate of about 10 to the power of minus 12 1 per second per the above considerations suggests that the deuterium-deuterium fusion rates in the range between 10 to the power of minus 23 1 per second to 10 to the power of minus 12 and 1 per second and higher can be considered readily observable subject to experimental details and specific reaction products. Comparing this range with the spontaneous fusion rate in deuterium-deuterium gas is almost equal to 10 to the power of minus 64 1 per second per deuteron pair at the molecular distance of 74 pm as estimated by Konin and Nunberg 1989. Based on the reference 20 sets a target for fusion rate enhancement of 40 up to 50 orders of magnitude. The next chapter would be in nomenclature when referring to deuterium-deuterium fusion. The nomenclature for deuterium differs across scientific communities and across different framing of the fusion problem. In nuclear physics, it is customary to refer a deuterium nucleus as a D and to a deuterium-deuterium fusion reaction as D plus D. Here, the occurrence of collisions with accelerated deuteriums is typically implied. The expression deuterium plus deuterium is also sometimes used to refer to a 2 plus 2 cluster configuration of nucleus in an atomic nucleus. See different states of the helium-4 nucleus as discussed in detail in section 4.5 and specifically in section 6.2. Other cluster configurations include the 3 plus 1 configuration of nucleus which serves as a precursor to what we refer to as a 3 plus 1 fusion. The various 3 plus 1 fusion points to deuterium fusion that results in either a triton 3 and a proton 1 or a helium 3 nucleus 3 and a neutron 1. It doesn't include the variant of deuterium-deuterium fusion that results in a helium 4 nucleus. The latter is of considerable interest throughout this document. For an explicit discussion of branching ratios, see 5.15. In chemistry and material science, deuterium atoms are referred as deuterium, which they form deuterium-deuterium molecules in the gas phase. In quantum dynamics, the deuterium pairs, such as in the case of deuterium molecule, can be viewed as a single quantum system with a specific energetic state associated with it. At the atomic and at the nuclear level, such a system can be referred to as absolute D2. In this article, we use the deuterium terminology as a D when referring to bare nucleus, such as in a collision framing. We refer to deuterium when describing a deuterium atom and deuterium when referring to a pair of deuterium atoms, which can be in the form of molecule D2. We use the absolute D2 terminology when a quantum dynamics framing is explicitly adopted, and to be highlighted in the most general sense, we refer to deuterium-deuterium fusion as deuterium-deuterium fusion phase that encompasses all conceivable framing of the process. The next sections and chapter would be earlier reports of energetic particle emission from metal hydrogen systems at low energies. A number of articles report observations of energetic particles emitted from the metal hydrogen systems simulated at energies far below those typical associated with the initiation of nuclear reactions. A selection of such articles and a brief summary of the reported observations are given below. In Chambers and his colleagues, 1990, the authors report the observations of charged particles with energies about 28 megaelectron-volt from the palladium foils that were bombarded with deuterium ions at energy less than 1.5 kilo-electron-volt. In Takahashi and his colleagues, 1919, the others report observation of neutron emission in the 3 up to 7 megaelectron volt range from the electrochemically loaded palladium deuterium samples stimulated by electric current pulses. In Menlove and his colleagues in 1990, the authors observed repeated bursts of neutron emission using high-efficiency neutron detectors in various forms of palladium and titanium metal in pressurized D2 gas cells and D2 oxygen electrolysis cells in Cameron Scholars in 1991. The others reports observation of is equal to 5 megaelectron volt charged particles from the bombardment of titanium foils with deuterium ions at energies of about between 350 up to 400 electron volt in ZM 2024 in reference 25. The other reports the observation of the 138 electron volt charged particles from the bombardment of palladium foils with deuterium ions at energy less than 500 electron volt. Chapter 3, Nuclear Fusion Rate Calculations. Here we review a standard approach to fusion rate calculation and show how it can be adapted it for the case of the spontaneous fusion of a deuterium pair. For example, in the form of deuterium complex, see section 6.21. We will also highlight the importance of electron screening for fusion and solid state throughout in the text. We will adjust our fusion rates based on experimentally observed screening values. We provide more details on the fusion rate calculations in 6.3. We also provide a GitHub hosted Python notebook to go to step by step through the calculations. It is a github.com project ida nuclear reactions. 3.1 Generals. Fusion can be described as a two-step process. One step is a quantum tunneling event through a potential barrier, with the barrier defined by the interatomic potential between two nuclei. The next section a relaxation or decay of the highly excited nuclei into some ground state or decay products with a concomitant release of energy. Step 1 is concept, which solving the Schrödinger equation to calculate the probability p that the nuclei have passed the Colombo barrier and are within each other's nuclear volume. Step 2 is concerned with the nuclear physics and proceeds at a rate gamma that's typically extremely fast, on the order of the 10 to the power of minus 21 per second. The fusion rate per pair of nuclei can then be simply written as tau is equal to p gamma. This two-step approach is most accurate way to calculate the fusion rates, and we will use it in section 6.3 based on the numerical integration of wave functions introduced in section 6.1. For the purposes of including the effect of electron screening, we will work with a simpler description, which is however commonly used fusion as a collision process, and we will adapt it to spontaneous fusion of two deuterons. The next section is 3.2 Fusion of a collision, a variety of approaches for performing fusion rate calculations based on the two-body tunneling model are provided by multiple authors. Reference 26, 7, 8, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. Central to all these approaches of fusion rate calculations is tunneling factor T that represents the probability of two fusing nuclears reaching the range of strong force attraction (FM range). T is also referred to as the barrier penetration factor. The tunneling factor TADA-UAE depends on the fusion reactant's proximity D as well as the screening potential in their vicinity UAE. The defining the difference between the received approach is the choice of the interatomic potential V, and to a lesser but still significant extent the choice of nuclear potential. The interatomic potential can be approached as a numerical potentials in the reference 20 and 39, or as a parameterized potential 4041 for numerical evaluation of the integral that determines the analytical expressions of the integral that serves as approximations are given by some others in 37, 40, 38. The collision picture, a fusion event occurs instantaneously when two nuclei collide with enough energy E to tunnel to within each other's nuclear cross sections. The fusion rate for the case of single nucleus colliding at a speed nu into a target with density L is the particle flux multiplied by the fusion cross sections tau is equal to n sigma T nu. Chapter 3.3 Spontaneous fusion from tunneling. Although there are no collisions in a spontaneous fusion of the deuterium in close proximity, we can adapt the fusion rate expressions in equation 2 through a helpful interpretation of n sigma nu without the tunneling factor. Sigma nu represents the reactable nuclear volume that's swept out by a colliding nucleus per unit time, and sigma nu then counts how many nucleus are in this reactable volume to give us number of reactions per second. The tunneling factor effectively reduces the density of particles in a reactable volume due to the repulsion between the nucleus. For the case of the deuterium complex of D2 molecules, the reactable volume is just the volume of the nucleus nu, NuC. The rate at which particles in this volume react is given by gamma. The density of nuclei is calculated by the inverse, the volume occupied by a single molecule 1 divided by nu mole. The effective density of nuclei and the reacting volume is T divided by nu mole due to the repulsion of the nuclei. This result in a fusion rate of tau is equal to nu divided by nu mole T gamma. Now I want to go through another sections, electron screening. In the first approximations, electron screening of nucleon can be expressed as a correction factor e to the power of minus r divided by r applied to the Coulomb potentials VR, where r is the screening length 42, 43, 44. The screening length in the term consists of a constant multiplied by n to the power of minus 1 divided by 6 when n is the free electron density of the metal. For palladium, n is approximately 3.15 to the power of minus 3. The resulting screen Coulomb potential is now expressed as VR is equal to Z1 Z2 e to the power of 2 divided by R e to the power of minus R divided by R. This approach requires assumption that the free electron density of the metal is treated as a Fermi gas. Applications of this approach of hypothetical system consisting of a D2 molecule within a palladium vacancy results in the contraction of interatomic distance from 74 pm or picometer to 57 picometer. The screening length all can be expressed as terms of a screening energy. U is equal to Z1 Z2 e to the power of 2 divided by R. For high beam energies, E is greater than UAE. The screening potential can be simplified to subtractions by a constant UAE. VR is equal to Z1 Z2 QA to the power of 2 divided by R minus UAE. The simplification is allowed because the classical tuning points for channeling satisfy R is less than R. In the high energy case, for very low energies, the full exponential must be used. Other considerations, such as the impact of positive ions on the screening potential as well as dynamic effects, can be introduced to Coulomb potential as additional corrections in reference 48. For the purpose of this discussion, they will be considered negligible and fusion rates will be considered through the context of a constant screening potential UAE as introduced above. A more detailed expression for the screening potential is given in Sersky and his colleagues in 2016. UA is equal to e to the power of 2, chi TF is equal to 2 e to the power of 3 divided by h, p 1 to the power of 1 divided by 3, TPN to the power of 1 divided by 6 square meter M star, where CarTF is the Thomas Fermi was wave number and the electron density, and M star the effective electron mass. In the first approximations, the effective electron mass is the electron rest mass ME. However, in some solid state environment, the effective electron rest mass is higher due to local electronic band structures change that results from the specific geometries. So thank you so much for watching my tutorial video until the end. If there is any simulations for this literature, you can find it from github.com/masterscript, github.com/kashiscript, or github.com/safrascript. Today is the third day of July 2026. Time is midnight.